Today we're fortunate to have Professor Russell Dupuis here with us to give his talk on work that he's done over the years. That's groundbreaking work that's really had a lot of attention. He received the Japan Prize in 2025, and as I was talking with him up here this morning, he also said that his advisor from Illinois received it in 1975, I believe. So, yeah, it's an interesting cycle 50 years later. So we're fortunate to have him on our faculty, and we look forward to his talk. So Russ, without any further ado, it's all yours.
Thank you, Bruno, and thanks to Jim and Helen Carreker for funding this lecture series. As my slide suggests, it's been about 59 years since MOCV was first demonstrated. I got involved in 1975 with this technology, and this is a photo of one of my early MOCV reactors that I sort of handmade at Rockwell International. In 2000, commercialized reactors had become fairly common. This is a picture of a Thomas Swan reactor made in the UK in 2000. It's similar to the reactors we have across the street in Bunker Henry in my lab. And in this 2025 period, these reactors have been further developed and are extremely large in capacity. This shows an Axtron reactor designed and built in Germany. So today I'm going to try to take you on a sort of historical trip along the path I call the traveling on the alloy road, on the path of how we developed, how semiconductors and alloy semiconductors were developed. So I'll start with an outline. As I mentioned, I'm going to try to describe how this whole concept of a semiconductor and 3-5 semiconductors developed, and the concept of alloys, the description of the MOCV process in simple terms, and the epitaxial reactors that were developed for that process. Then I'll move into the device applications where this technology really dominates the commercial field today. I'll talk first about solar cells and injection lasers grown by MOCVD, and then I'll talk about a very interesting development of quantum well laser diodes. These are lasers that use quantum size effects of ultra-thin layers and the quantum mechanical particle-in-a-box solution that you all know from your physics. Then I'll move into the LED technology and the markets, move in later to optoelectronic systems and power applications of MOCVD 3.5 devices, and then I'll speculate a little about the future impact. Let me start with this. Some of you may know this quote, "One should not work on semiconductors. That is a filthy mess. Who knows if they really exist?" So this quote isn't from some random person on the web with a blog. This is from Wolfgang Pauli, the author of the Pauli exclusion principle. In 1931, he went on the record saying, "Semiconductors don't exist and they're a mess, so why bother?" Well, there is Wolfgang. Fortunately, not everyone followed that description, and Alan Wilson at University of Cambridge, the same year, 1931, published the first quantum mechanical description of band theory and explained how semiconductors actually work for the first time. So fortunately, in 1931, we can talk about people finally understanding these materials, which were discovered long ago. They're part of the Earth's crust. Lead sulfide is a semiconductor. You can dig it out of the ground, and people were using it. It was called galena in the metallurgical sense for point contact rectifiers. There are many milestones in this history. Like in any technology, there are lots of people contributing, but I'm going to pick out a few things here. The first description of the term semiconductor used as a noun. Anyone have an idea what year that was? Guess? No? 5 BC? It was actually in 1838 where this term appears in a journal published in London in the Annals of Electricity, Magnetism, and Chemistry. So this term is now, of course, well known, but it had to be invented, obviously. The first observation of rectification in a semiconductor, anyone have an idea? Should be a famous thing. Bruno, what do you think? 1874, Ferdinand Braun, you may know Braun Electrical Company still exists, that's his company. And he observed, as I mentioned, rectification in lead sulfide crystals that were dug out of the earth. They're part of the Earth's crust. First use of the term epitaxy. Anyone? Alan, what do you think? It's actually not that old. 1928 is when a Frenchman, Louis Royer in France, who's a mineralogist, looking at the growth of various crystalline salts like gold chloride on other crystalline salts. So it was actually in French, of course, l'epitaxy. He's the one who first used that term. P-N junction, I think everyone knows this, right? This is 1940, Russell All, a double E at Bell Labs in Homedale. There's a small building in Homedale where this lab was located. He accidentally discovered the P-N junction when he was trying to purify silicon. And there's a long story about this, so you can read on the web, but I won't go into it. This is, everyone I think knows this, right? My students know this. When was the transistor invented? They don't know. Anyone? 47. This is Walter Brattain and John Bardine's invention on November 16th, 1947 in Murray Hill, New Jersey. And they were looking at a point contact device that I'll describe. It was made from a repurified crystal of germanium that was produced at Bell Labs. And how about the first laser diode? First laser is 1960. It's a ruby laser, flash pumped. 2 years later, 1962, Robert Hall at General Electric in Schenectady, New York, demonstrated the first gallium arsenide laser diode, which was a diffused P-N junction with a fabricated, manually polished cavity operating at 77 Kelvin under pulse conditions. So those of you today who benefit from laser diodes and the web, you should think about and thank Mr. Hall. So my point in all of this is that the transistor was the turning point in changing the semiconductor from a curiosity like lead sulfide galena crystals with point contacts for radio receivers to an industry. Suddenly people had the impetus to study this material and to study its properties both fundamentally from theory and experimentally from doing device work, doing diffusions, looking at improving materials. So the foundation, I believe, of much of our work, in fact, most of our work in semiconductor devices today is built on the first transistor invented by John Bardeen and Walter Brattain. In fact, Bardeen in 1947 was the first person to identify the role of minority carrier injection in a semiconductor, and the role of the minority carriers is dominant in the P-N junction, as you all know. We have majority carrier devices, of course, like FETs, but fundamentally that observation of distinguishing minority and majority carriers was an important innovation. This is a picture of the first transistor. It's a point contact device, as I said, fabricated in a recycled piece of germanium that had been used in other experiments. And they invented the terms emitter, base, and collector in describing this device. Later on, in January of 1948, Bill Shockley at Bell Labs published the first mathematical description of the P-N junction, minority carrier injection, and the properties of the NPN and PNP transistor, which still use the same physics. Have emitter, base, collector, the same minority carrier and majority carrier issues that arose in the first point contact transistor. So, as I mentioned, November 16th in 1947, Walter Brattain is the first person to observe transistor action in a semiconductor. It wasn't announced until June 1948. It was considered a secret by the US government and by Bell Labs. They obviously wanted to get their patents all in order. And this cover picture appeared in September 1948 on Electronics magazine, which was the dominant, if you will, publication of the industry at the time. And you can see here John Bardeen Walter Brattain and Shockley, and it looks like John and Walter just sort of popped in on Bill's lab and said, "Hey, Bill, what are you up to?" It's Shockley's experiment. He's operating the probes to measure his transistor. It's clearly Shockley's experiment. These gentlemen got the Nobel Prize in Physics in 1957, but it wasn't Shockley's experiment. It was Walter Brattin's and John Bardine's experiment. Although, as I mentioned, because Shockley observed this process of minority carrier injection, and Walter and John explained to them what they were doing, he locked himself up in a room, literally on New Year's Eve was working on these equations, didn't go to the parties, stayed in his room at this swanky hotel he was at, and worked on these mathematical formulas. And so he published the minority carrier diffusion equations in 1948. This is a more accurate picture of the real experiment. It's got Walter as the experimental researcher in Walter's lab with Walter's apparatus, John, the theoretical man, his collaborator, taking notes, and the passive observer, Mr. Shockley, who wandered in from the hallway to see what they were doing. So in many cases in the past, people have thought about this and said, well, why does Shockley get a Nobel Prize for Walter and John's experiment? And it's because of his mathematical analysis of the NPN and PNP transistor. All of you know about semiconductors. They exist primarily around column 4 in the periodic table. Silicon and germanium and their alloys are the dominant form of semiconductor in our universe today. But you all know that we can also use 3-5 elements with an average of 4 valence electrons to create semiconductors. The prototypical 3-5 is gallium arsenide. If you add phosphorus, you get a ternary alloy. Those phosphorus atoms go on the same sublattice as arsenic atoms. And this is the first ternary that made a visible LED, gallium arsenide phosphide, red LEDs and laser diodes. If you add aluminum, you get a quaternary. This is the first quaternary aluminum gallium phosphide arsenide demonstrated by Nick Holonyak's group at Illinois in around 1977, or earlier, 1970, sorry. If you add indium, antimony, nitrogen, boron, you get all of these nice materials. They're all semiconductors. You can make quaternary alloys. Clearly, you can make 5-element pentanary alloys, although today there's no practical pentanary alloy in commercial production. So 3-5 alloys sort of dominate our space now. It's not the binary components that we're interested in as much as the alloys. So I've created this little timeline of what I consider our historical development of 3-5 compound semiconductors, and particularly focusing on alloys and epitaxial growth. As I mentioned, 1931, semiconductors finally exist. They're understood in some fundamental way. 1940 is the first PN junction, accidentally discovered by Russell All. 47 is the first point contact transistor, and 48 the PN junction equations for NPN and PNP BJTs. 1950 is the first announcement that 3-5 semiconductors exist. So this was basically work by Welker and Siemens in Germany, although others contributed to it. As I discussed earlier, the NPN and PNP transistor created the need for control of doping in 3 regions, the base, emitter, and collector. That led to the development of epitaxial growth, in particular vapor phase epitaxy first, for silicon, germanium, gallium arsenide, indium arsenide, and then the ternaries, gallium arsenide phosphide and indium arsenide phosphide. And a few years later, LPE for gallium arsenide, and a little later in 1967 for aluminum gallium arsenide. 1962 was a banner year for semiconductors, the first semiconductor laser, as I mentioned, by Bob Hall and gallium arsenide and GE, and the first high-efficiency infrared emitting LEDs. Also, Professor Holonyak then at GE in Syracuse developed the first red LEDs and the first red laser diode. So 62 was September, October. Within a month, we had 2 laser diodes, the gallium arsenide first in September, and in October, Holonyak's red laser diode. The availability of epitaxial growth led to the development of heterostructure devices, in particular LPE of aluminum gallium arsenide and aluminum gallium arsenide phosphide, as as I mentioned. In-gas laser diodes were developed. In 1967, MOCVD was developed, and the same year, roughly, MBE was first described. This led to, as I earlier referred to, the first quaternaries in 1970, aluminum gallium arsenide phosphide, and the first infrared emitting quaternary, indium gallium arsenide phosphide in 1976. In 1981, the first aluminum indium gallium phosphide for red and yellow LEDs. So these developments over this period of many years led to, in the 80s and 90s, what I call the analog, solid-state device analog of the Cambrian explosion, where we have a variety of devices being created, most of them containing heterojunctions and a lot of them containing alloys. So I have this alloy road that I've proposed. This is my description of the Cambrian explosion of the alloy road enabled by epitaxial growth. While there are many workers on there, many events, I'm going to pick a few milestones. First, as I said, I believe the bipolar transistor was the impetus to bring forward epitaxial growth, to bring into our environment control of doping and precise alloy compositions. And that led, based on minority carrier injection and understanding of the properties of a p-n junction, to interest in 3,5s, the first ternaries in 3,5s in 1955, the development of 3,5 epitaxy in 1960, the gallium arsenide phosphide red LED and gallium arsenide phosphide red laser diode, the 1970 3,5 quaternary, the 1970 lattice matching using quaternaries and ternaries and binaries, indium gallium phosphide laser in 1971, which gave us a wide bandgap semiconductor that could emit yellow light under some conditions, and more efficient red. The quantum well laser in 1977, the VCSEL vertical cavity surface emitting laser in 1979, imperial-induced layer disordering in 1988, the native oxide of 3,5 semiconductors containing aluminum in 1990, the 1994 quantum dot laser, the 2004 photonic integrated circuit, the 2010 silicon on 3,5 integration going commercial, the UVC laser diode in 2019, and today and the future, 2026. So this is about 7 years of research on the alloy road, and this, by the way, is a real road. You can drive it in Italy. It's the Stelvio Pass in the Italian Alps. So you can see my concept that this technology keeps moving forward with several important twists and turns, giving us higher power design space. So today, our markets increase rapidly for semiconductors. The global semiconductor market in this year is expected to be about $900 billion, heavily driven by demands for AI. And our industry is forecast to reach $1 to $2 trillion by the 2030s, with a projected market cap last year exceeding $12 trillion for the companies involved in this. So my concept is that we have this big elephant in the room, silicon, and we have this smaller player, 3,5 semiconductors, $750 billion market for the elephant and $120 billion for the young lady. And certainly the elephant is intelligent and powerful, but the young lady is more intelligent, more flexible, and more clever. And so she does a lot more and can do a lot more in the future than our friend the elephant. And that's sort of my basis of the claim that 3.5s actually underpin what silicon is doing today in many, many applications. So obviously silicon has become a low-cost, high-volume production technology based on CMOS and its derivatives since the beginning of CMOS at RCA. They're ideal for electronic devices, microprocessors, memory chips. And so I have this Swiss Army knife for silicon that I'm going to propose to you. And its tools, its blades, have solar cells, integrated circuits, power devices, photodetectors, silicon photonics, and sensors. And this knife you can buy on Amazon for $24. It's obviously quite useful. does a lot of things. My Swiss Army knife for 3.5 semiconductors, though, is much more capable. And so when you look at what you can do with this tool, you have light-emitting diodes, laser diodes, transistors, LiDAR, radar systems, solar cells, photodetectors, thermophotovoltaics, radio frequency electronics, light wave modulators, power electronics, single photon sources, photonic integrated circuits, and sources for silicon photonics. This Swiss Army knife you can't buy today because it's out of production, so if you can find one, you should buy it because it's a big investment. It would cost you about $1,400 if you could find one on the market today. So my point in this is that while silicon is useful and has a lot of important applications, there are many more things that we can realize with semiconductors that are composed of 3.5 materials, and especially alloys. The first commercial 3.5 semiconductor LEDs and lasers were announced in 1963 by General Electric. And most of us know General Electric doesn't make LEDs anymore today. But the original prices were $2,600 in $63 for the red laser diode and $700 for a single red LED. This panel on the right here is the Allied Industrial Catalog from 1965 showing these new prices. They reduced the price by 50%, already 50% reduction in 2 years. So you could buy an IR infrared laser diode for $650 and an IR LED for $45. Visible laser, again, only operating at 77 Kelvin, was $1,300, and a red LED was $135 each. Corrected for today's inflation, that's $1,400 in today's money. Today, a much brighter gallium arsenide phosphide LED costs about 2 cents, a factor of 70,000 less than 1963's $1,400 inflated price. They still make gallium arsenide phosphide LEDs today for the really cheapest possible applications. But obviously we need a better emitter than gallium arsenide phosphide and heterojunction systems, so people have moved to the quaternary aluminum indium gallium phosphide for red, orange, and yellow light emitting diodes and laser diodes. This plot many of you are familiar with is the energy band gap on the y-axis versus lattice constant of the crystalline structure. In this case, it's cubic or zinc blende on the x-axis. And if you look at the gallium arsenide lattice parameter and its projection up into the quaternary space, you can see we can make very nice red LEDs, amber LEDs, yellow LEDs, but sadly we can't make good green LEDs because it's too close to the direct-indirect band gap crossover. So we have to find another solution for green, blue, and UV LEDs, and that solution is the quaternary aluminum indium gallium nitride. Again, band gap energy versus lattice constant. In this case, it's a Wurtzite crystal, so this is the A-plane lattice constant. And as you can see, there's no good way to make a lattice-matched green LED because we don't have a substrate of indium gallium nitride yet, although Alan's working on that, I think. He has, at least. At any rate, so you can grow these materials on sapphire, which Hal Manasseh was the first person to do, by the way. And so you have a substrate that's fairly large area. In fact, 12-inch sapphire exists today for green LEDs, blue LEDs, and UV LEDs. And more recently, we have bulk aluminum nitride substrates and bulk gallium nitride substrates to use for this technology. So let me move now to the MOCU process itself and the epitaxial reactors that have been developed for both the research and the commercialization of this technology. I want to mention again Hal Manasseh, who was the first person to use this process and develop this process and indeed tried to patent the process, but he was not successful in patenting it. His first work began in 1967. Where he was growing gallium arsenide on sapphire, beryllium oxide, spinel, various insulating crystals, and it was first published in January of '68. Manasseh was a PhD chemist, inorganic chemist, and he was looking at heteroepitaxy on insulating oxide substrates for, I won't go into the details, but he had a really good reason for wanting to grow on insulating oxide substrates. This was the only technology that could do that. And here's a picture of Hal about the years when I started to interact with him and knew him in 1975. So this process is very simple. It's a pyrolysis process. I've got a cartoon here. I'll go through it quickly because most of you probably know what's going on here. We have a reactor chamber. In this case, it's often stainless steel in today's technology. And we have a substrate at around 1,000 degrees. We introduce trimethylgallium, a simple methyl compound with 3 methyl radicals on a gallium atom. That gets pyrolyzed. And then we also inject ammonia, NH3, a nice simple molecule with hydrogen, 3 hydrogen and nitrogen. And those react again on the surface to form a thin layer by diffusion and then a surface reaction, forming gallium nitride and 3 moles of methane as a byproduct. Methane is stable at this temperature, so it's just swept out by the main carrier gas flow into the pumps. So using this process, we can build up a crystal layer by layer. Well, Mother Nature does this for us because always seeking the least energy position for atoms on the surface. And we've given enough energy by heating it to 1,000 degrees. In this case, in the gallium nitride case or the indium aluminum gallium nitride case, we get a hexagonal crystal. And with that technology, we can easily grow in GaN LEDs as shown here. So reactor development has followed an interesting path as well, like the technology of the alloys, beginning in 1967 in my cartoon with essentially one of Hal Manasevit's reactors, or one like it. Atmospheric pressure, vertical chamber, rotating disk of a few RPM, and hydrogen as a carrier gas, RF heated. In 1975, Sidney Bass in the UK developed a horizontal version of this. This is the so-called Bass cell that dominated the UK's development of MOCVD. Simple horizontal reactor with a slightly tilted graphite susceptor, RF heated, again, atmospheric pressure. A big change occurred in 1978 when Jean-Pascal Duchemin and his co-workers at Thomson CSF near Paris developed a low-pressure MOCVD. So they have a similar Bass cell, horizontal reactor, slightly tilted susceptor, but they brought their chamber to low pressure by using a vacuum pump. Interesting sub-story, the first time they did this, they pumped all the TMG out of the bubbler and into the pump because they didn't realize they had to have a pressure controller, because Duchemin had developed this process first for silicon using silane, a gas source. He wasn't familiar with liquid sources, so interesting times. Another important event occurred in around 1986 or so when Christine Wong and her co-workers at MIT Lincoln Laboratory did the first detailed flow studies of a vertical stagnation point flow reactors, as shown here. They did both simulations and experimental work showing that you could develop beautiful, perfect laminar flow in a low-pressure MOCVD reactor under certain conditions of temperature and pressure and rotation rate. So this opened people's eyes to the fact that we have control over the gas phase, pressures, chemistry, surface concentrations to be able to do very large area uniform epitaxy. And so these two elements of our technology were combined to make large-scale commercial reactors in the 2000s, beginning with the turbo disk developed by EMCOR in the US, the showerhead developed by Thomas Swan in the UK, and the planetary reactor developed first in France, then commercialized by Axtron in Germany. These reactors are increasing in size almost as we speak, and 2010, 2020s, the capacities were becoming ridiculously large because the demand for epitaxy and lower cost devices was dominating the marketplace. So today you can buy any of these nice reactors. There's Vico Turbodisk from the USA, Axtron G10 from Germany, the Advanced Microfabrication Equipment in China, and Nippon Sanso in Japan. They're all basically the same technology, but developed in different ways for commercialization. These systems cost you $6 to $8 million depending on your options. So let me turn now to device applications. And as I mentioned earlier, the heterojunction technology for devices is already in development. What was lacking was a way to make that technology commercializable at low cost with high yield. People had tried MBE, LPE, and vapor phase epitaxy. There were limitations to all of those, fundamental limitations in some cases. The first device made by MOCVD was an FET, actually, made by a group at Rockwell International using HAL's gallium arsenide on sapphire. So it was a gallium arsenide MESFET, but not an optical device. So I want to talk about optical devices because they largely where I spent my career. The first optical device was a solar cell we published in 1977. It's a heterostructure device, simple AlGas window heterostructure PN junction as shown on the left. In the center you see the air mass zero photoresponse of this device using what then we had was a solar simulator simulating the spectrum in outer space, air mass zero, under one sun illumination. And on the right you see a solar cell wafer that I grew, well, the picture says 79, so let's say early 79. It was the largest solar cell wafer produced at the time. It's the largest piece of gallium arsenide you could buy that was low dislocation density. This was horizontal Bridgman grown gallium arsenide. And you can see 1 square centimeter cells fabricated on this device. So this is the first report of a MOCVD grown optical device. At almost the same time, LPE was being used for AlGas solar cells, and they were limited to maybe 1 or 2 smaller pieces, maybe 1 inch square in the LPE boat. So in 1977, when I published this paper, most of these devices were grown on 10 to 15 square centimeter substrates, and in my paper I predicted that this would be scalable by MOCVD to over 200 square centimeters of substrates in a single run. Well, today, large capacity reactors like the ones I showed you are common. This is an Extron AX G5C+, first developed in 2016, 40 years later. It has 5 200 millimeter diameter wafers per run. It's greater than 300 square centimeters of epi per run with high uniformity and high yield. So they've exceeded my predictions pretty well. In fact, there are now larger reactors in production. In fact, there are estimated to be about 4,500 MOC reactors in production today, a lot of them in China. What about solar cells? Well, this is a plot of the solar cell performance efficiency on the y-axis versus year, developed by NREL, and covers the period 1976 to 2025. All of the record efficiency 3.5 solar cells or solar cells of any kind are grown by MOCVD, and this is the space that people are working in today for high efficiency cells. In fact, the MOCVD grown multi-junction cells are critical power sources in space. All of NASA's near-Earth orbit satellites and systems use MOCVD grown cells. This is one of the early applications. In this Hubble telescope, as you know, was launched in 1990 with silicon cells, and they were replaced by a space shuttle repair mission to gallium arsenide multi-junction cells in 2002. Another important system were the 2 rovers, Opportunity and Spirit, on Mars. These were launched in 2004 with gallium arsenide triple junction cells grown by MOCVD. Another application is ISS, the International Space Station. Since 2021, the cells are being replaced, the silicon cells are being replaced by gallium arsenide multi-junction cells grown by MOCVD. They were first tested in 2001. So 2001 was actually the first space phase test of these multi-junction cells grown by MOCVD, and they were so successful that they've started to move everything to MOCVD multi-junction cells. More recently, in 2021, the James Webb Space Telescope was launched, and it has, again, multi-junction cells grown by MOCVD. So all of these high-end space platforms are using MOCVD triple junction cells. Let me turn now to the light emitters. The first injection lasers, as I mentioned, were 1962. They were diffused junction, homojunction gallium arsenide devices. Algas lasers appeared around 1969 and 70. In 1977, we published the first MOCVD grown laser diodes. They were aluminum gallium arsenide double heterojunctions. You see in the SEM picture there on the left-hand side, and on the right, the spectrum. These were room temperature pulsed lasers. So they weren't low temperature like the first gallium arsenide lasers. They were room temperature. And this report sort of shocked the industry, because at the time, people thought LPE was the only working technology. MBE was being developed, and so there were some examples of MBE lasers. They weren't reliable, though. They couldn't meet the requirements of the Bell system in reliability. So this gave another option for developing lasers. And in fact, as I'll discuss now, the first quantum lasers. So these lasers that were existing in up until about 1977 were heterojunctions with layers on the order of maybe 300 to 200 nanometers in the active layer. That was limited by LPE production technology. So people who had access to MBE systems were excited to try to develop a new series of lasers that used quantum size effects. And this is the result, the first quantum size effect laser, optically pumped only, no diode, at low temperature only, at 15 Kelvin, by Van der Zeel and his colleagues at Bell Labs Murray Hill. And they reported aluminum gallium arsenide based double heterostructures. As you can see, they had grown 50 pairs of 8 nanometer thick gallium arsenide layers with a smaller band gap, surrounded by larger band gap aluminum gallium arsenide 20% aluminum layers. And they show, as you can see on the right side, optically pumped spectrum at 15 Kelvin with 2 wavelengths, one for the gallium arsenide band gap emission of the substrate, and then the shorter wavelength quantum size effect emission of the superlattice. I want to point out, if you look carefully at this paper, you'll see there is no definitive proof of lasing, even though they claimed, as in the title, laser oscillation. They might have had stimulated emission, but even that wasn't proven by their data. So I'm still skeptical about this, and unfortunately, all those people are dead. So you can't ask them. At any rate, the point was that we have an exciting new concept of a laser with ultra-thin quantum well, multi-quantum well, multiple thin layer active regions. And at this time, MBE was, if you will, the premier technology for these kinds of thin layers. So who made the first quantum size effect laser diode? Well, actually, it happened in May 1977. It's, again, at low temperature, pulsed. And the question came up after these results came out, and IBM was doing similar things on superlattices for carrier transport, tunnel diodes, etc. Leo Isaki was looking at tunneling. And the question came up is expensive MOCVD system required to grow quantum size effect heterostructures? And Professor Holniak, my advisor at Illinois at the time, I was graduated, but he said the crystal does not know how it's grown, so what the heck, let's give it a try. So instead of this type of research MBE system, he didn't have the money for that, he moved to what they had, a small LPE reactor with some grad students that, if anything, you can tell was pretty cheap. Today, that MBE system would cost you about $2-3 million, depending on how many Knudsen cells you order. But the LPE reactor would cost you about 1 to 2K today. So it's that kind of ratio was existing in 1977 when this work was done. And no one believed that LPE could grow a quantum size effect layer reliably and reproducibly. Holniak's team went even several steps further. They not only grew a trivial gallium arsenide quantum well, they grew a quaternary quantum well, a quantum well of indium gallium arsenide phosphide. I'm sorry, it's aluminum, indium gallium phosphide. So here's their paper from 1977, the first two-dimensional quantum size effect laser diode operating at 77 Kelvin, pulsed again, and not CW. And you can see the spectrum here. This was an LPE quaternary 20-period quaternary quantum well with 5 nanometer thickness operating at 77 Kelvin. Again, this is infrared, so you see the wavelength's about 1 micron. And this sort of shocked everyone when they read this. How could LPE do this? And there's 20 layers and they're quaternaries. How crazy can you be? Well, this work was first reported in June of 1977 at a conference I attended, the famous IEEE Device Research Conference in late June. And it was a late newspaper submitted after the normal abstract. Our first double heterojunction laser grown by MOCV was submitted to the same conference, again as late newspaper. And so we were talking to each other on Sunday before the conference started. Holniak was on the review committee, so he knew my late newspaper result. And he said, "How did you do that, Dupuis?" And I said, sort mumbled a few things. He said, "Well, let's collaborate." So 4 months later, we had the world's first quantum laser diode operating at room temperature. I grew it in my lab with that little MOC reactor you saw, and it was processed and tested by Holniak and his students. The first MBE-grown quantum laser diode was not achieved until about 18 months later by Wantian Sang at Bell Labs in Murray Hill, and it had a higher threshold current density. So, in fact, we were 18 months ahead of all the MOCVD groups as well. So it was 18 months before anyone had a quantum laser operating at room temperature besides our work. And this is the result. As I mentioned, this is a single quantum well. I didn't need 5 or 20 or 50 pairs for enough gain. I had enough gain on one quantum well to get a laser. And not only that, it was 20 nanometers. And as you can see in the spectra, the quantum size effect shift was dramatic from 870 nanometers, where the band gap of gallium arsenide is at room temperature, to 790 nanometers in the upper quantum state. So we saw not only the first quantum transition, heavy hole to electron to heavy hole, we had light holes, we had the second quantum state, the third quantum state. We were seeing a whole plethora of quantum state emission from these quantum wells. And so this changed people's ideas about MOCV pretty dramatically. As a result of this, the quantum well laser diode market is going to be about $14 billion by 2029. You can see this plot of the growth of this. Well, all these are quantum well lasers. There's no double heterojunction lasers sold today. They're all quantum well lasers. And so you can see our dominant application is optical sensing and data storage and communication. And that's going to continue to grow dramatically as AI starts to build infrastructure on the planet. So what about the next step? Well, right now, MOCVD quantum well laser diodes have over 95% of the market value. Probably going to continue to increase their market share. There's still important applications for MBE-grown quantum well lasers, particularly in some of the quantum size effect devices that are developed over many years by many people, but Capasso and others are the first ones to make these quantum cascade lasers. Let me now turn to the LED, which you're all very familiar with, I'm sure, but I'll try to describe a few things that maybe you didn't know. This is a plot of the visible light emitting diode performance in lumens per watt versus year. As you can see by the red curve, roughly that curve progresses about 10 times per decade, an increase of 10 in performance per decade. Important points to note: the first Edison light bulb was about 1 lumen per watt. The unfiltered incandescent 60-watt light bulb is about 20 lumens per watt, and a normal fluorescent lamp is about 80 lumens per watt. So what you see here is some dramatic change around this period of 87 or so. Things moved from ternaries and binaries to quaternaries, and that technology change coincides with a shift from vapor phase epi and LPE as the production technology to MOCVD. So almost as a, you're driving along in the car and you take a left-hand turn and everybody follows you, and that's what's happened here. So there's a technology divide in LED technology in terms of materials technology. There's also another divide, which is this line here. All of these LEDs on the right side are quantum well LEDs. They all have quantum well active regions, just like the laser that I described earlier, similar at least. So another important point is it took till 2006 before a white LED made by conventional technology with phosphor and a blue LED pump reached the performance of a fluorescent lamp. So 2006 is sort of the tipping point for fluorescent lighting. LED dominated incandescent before that time, but now they're able to wipe out fluorescent lamps in terms of cost performance. And interesting to note, MOCVD took about 19 years to enter into the dominant technology for LEDs. Quantum wells, the first quantum well laser diodes, 1978. And that took about 14 years to become the dominant device technology for LEDs. 2006, an important year. After 4 years of development, we have a white LED that can compete with all these. I don't know, these are fluorescents or not. Can't tell. An important year also because Queen Elizabeth II's 80th birthday was 2006, and so the Royal Palace decided to light the exterior of Buckingham Palace with white LEDs, and they contracted with Philips Lumileds to install the white LEDs on the facade of Buckingham Palace. You can see this nice picture here from 2006. So the Queen has given her stamp of approval on LED technology, and everybody can be happy it's got the stamp of approval. I'm told that this lighting cost less than $2 per night at the time. Of course, energy prices have gone up, so I don't know what it is today. So in the past few years, this plot is from 2022 to projected 2030. The global LED market is going to increase from about 110 billion in 2026 to 165.4 billion, with a compound annual growth rate of 11% by 2020. Virtually all of these devices are going by MOCVD. And if you look at markets, about 66%. There's still some, strange enough, some really cheap infrared LEDs made by LPE. And still, as I mentioned, some gallium arsenide phosphide LEDs made by vapor phase epitaxy. Let me now turn to broader applications for optoelectronic and power devices grown by MOCVD. This shows the global 3.5 materials market value for optoelectronic and power devices versus year from 2023 to 2033. You can see that this is dominated by applications for consumer electronics and telecom. It has a compound annual growth rate of about 10%, and its market size estimated about $2.8 billion in 2033. It's dominated by GaN, secondly by gallium arsenide, and thirdly by indium phosphide and others. So the GaN technology, because of its applications to lighting, lasers, power electronics, is becoming a dominant component of the materials market grown by MOCVD. Some of you may know that your Apple iPhone, like I have here, is powered by MOCVD. This is the iPhone 10 in 2017 introduced the face recognition components. That's a picture of the top of an iPhone 10. And on the right, you see a breakout of this array of components that form the face recognition application. First, we start with a flood illuminator, infrared light illuminator grown by MOCVD. Then you put your front-facing camera to analyze the light reflected, and it confirms there's a face. And then the IR VCSEL dot array projector in orange projects about 30,000 dots onto your face to create a three-dimensional map. And then the IR camera in blue reads that map and confirms it's you from the reflection of those dots. So all of this stuff is MOCVD stuff. And so the iPhones, you can't open your iPhone without saying hello to MOCVD. Let me turn to the intergalactic network. Right now, the intergalactic network runs primarily on indium phosphide-based PICs, photonic integrated circuits grown by MOCVD. You see on the left here an Infinera PIC with 10 discrete wavelength distributed feedback lasers, very precise wavelengths and spacing. There's about 700 optical and electronic components on that chip, and they're all grown by MOCVD through several selective area regrowth steps. They have about 80% of the market share right now for the kind of interconnects that are long haul. There's a compound annual growth rate expected of about 20.5% in the 10-year period from 2021 to 2030. It's about $4 billion market in 2030. North America has the largest share right now, about 45%. And the growth drivers in the lower panel are data center, biomedical, electronics, telecom, autonomous vehicle industries, and artificial intelligence. So everything you do, everything you touch beyond your phone goes through some sort of an MOCVD process, at least as it goes farther down the line beyond the local area system. So you all know that our internet traffic is global. It runs on mostly undersea cables right now. There's a zillion of those cables. Some of them are being destroyed by Russian freighters dragging their anchors across the floor to kill your communications in selected places in the North Sea. But we have to repair those, obviously. But most of these undersea cables, or virtually all of them, run on MOCVD devices. And the internet is, of course, a primary creator of the economy in most countries today. This is an example of the Intergalactic Computer Network, or Internet Use versus Time, taken in February 2025, beginning, as you can see, in 1990. 1963 is when the Intergalactic Network was conceived by ARPA, by a guy named Licklider at ARPA. And at the time, it was just computer to computer. And of course, the first commercial website opened in August of 1991. And so the growth that's occurred now is about 5.56 billion users, individual users. The Earth's population last year was about 8.2 billion. So about 67% of the Earth's population used the internet last year. And all of that, again, runs on largely on MOCVD devices. This is a plot from the same month, February 2025, of the daily time spent using internet by age and sex, assuming there are two sexes. So beginning on the left, you see younger females dominate the use for about 7 hours and 35 minutes a day. And on the far right, male, old guys like me, 3 hours and 59 minutes per day. So almost a factor of 2 difference. The dashed line there may be where the baby boomers fall, that orange dashed line. Anyway, so the point is that a lot of people are using this. And as I mentioned, it has the dangerous problem of being able to be destroyed pretty easily by dragging your anchor along the ocean floor or sending a bot down, undersea bot down to destroy those cables. So we have an alternative, space-based telecom. You all know about SpaceX. SpaceX Starlink is ultimately going to have probably over 12,000 low Earth orbit satellites. All of those rely on MOCVD, not the cells, not solar cells, but everything else. The RF microwave electronics, high-speed secure optical links, and selectively power electronics are all based on MOCVD, but not the solar cells. Mr. Musk wants to use cheap solar cells because he knows his satellites are going to need to be crashed and then redeveloped with more features. So he doesn't plan for a long life of his LEO satellites. Gallium nitride devices are used for high power RF and millimeter wave power amplifiers. Gallium arsenide is RF, monolithic millimeter wave ICs, low noise amplifiers, phase shifters, and some power amplifiers. And indium phosphide lasers are used and other detectors and receivers including PICs, for photonic devices for inter-satellite optical links. Another place for GaN grown by MOCVD devices is power electronics. Obviously, silicon carbide is a competitor in that space. It's a compound semiconductor, about 3.5. But of course, GaN devices have higher efficiency. They have higher electron mobility, and that gives you higher switching speeds and reduced energy loss. They are actually more compact than silicon by far, and lightweight, and have better heat dissipation than silicon. And they also allow higher voltage operation. So today you can buy cars with GaN, you can buy power blocks, you can buy plug converters, all based on GaN power switching devices. And that market's going to grow a lot. Oops, I didn't want to do that. Projected market size in 2030 is about $13 billion with a compound annual growth rate of 27.4%, as shown in this study that was made by a research company. They say it's about 3.1 billion in 2024 and growing to 12.5 in 2030. So let me now try to address the future. Hard to address the future with the world on fire today, but this is a plot from the web again of the technologies based on gallium arsenide, indium phosphide, gallium nitride, and silicon carbide that are likely to impact or have impacted our technology for electronics and light emitters. So you can see gallium arsenide LEDs started back in the 70s, indium phosphide LEDs around the 80s, and then GaN-based LEDs around middle 90s. Silicon carbide is coming along here with the first 400 volt and then 800 volt devices. All of these are MOCVD technologies. They're all based on MOCVD. And in fact, gallium nitride is in production for 800 volt EVs now. So you can buy a GaN powered car. Well, what about CMOS and all that elephant stuff I described earlier? Well, obviously, our shrinking technology, the Moore's Law, so-called Moore's Law, is becoming more difficult and more expensive, and you have to have deep UV lithography tools, which are $1 billion a piece or something. I/O itself is causing a power problem, too much resistance, too much heat. So we need a whole new set of approaches, and I'm sure you know that the solution is the integration of 3.5 compound semiconductor devices grown by MOCVD with silicon-based CMOS. So system on integrated chips and chip on wafer on substrate. This is a plot from Tokyo Electron showing the density per square millimeter versus year of the interconnect pitch and interconnect pitch and density. And you can see how these different approaches have matured, and we're approaching the space where SOIC is dominant, and monolithic 3D will become standard in the future. And that will look something like this. Concept of an SOIC integration of MOCVD 3.5 devices with silicon integrated circuits showing GaN-based and AlGaAs and 3.5 various devices, primarily GaN and InGaAs devices embedded on a larger area CMOS chip. So what about the future beyond that? Well, on to Mars. We're going to go on to Mars. MOCVD devices are required, I claim, for human occupation of Mars. You're all familiar with growing potatoes on Mars, I think. And that used MOCVD-grown LEDs powered by MOCVD-grown solar cells. You might know that the sun is a little bit farther away from Mars than it is from the Earth, and it has about 70% less, 50% less energy at noon, and it has a dusty atmosphere, so that even reduces things more. On a clear noon surface on Earth, you have about 1,000 watts per square meter, and on Mars, in the same conditions, you have about half of that. And also, the global average over day, night, and latitude is much lower, so typically on Mars, you have more like 150 to 250 watts per square meter. And dust storms can reduce the surface sunlight on a solar panel by 50-90% for weeks. So you better get your world's best solar cells up there and your world's best LEDs, and they're all going to be by MOCVD. So in summary, I'm trying to pretend that you now understand, I hope you understand, that MOCVD first developed around 1967 is a dominant materials technology today in commercial and research use for 3-5 compound semiconductor heterostructure devices, that important terrestrial and space applications rely on this technology, including LEDs, laser diodes, photodetectors, photonic integrated circuits, the intergalactic network, Starlink, AI systems also rely on MOCVD devices, and it also dominates certain sectors of defense electronics markets and provide key technologies and capabilities for advanced security systems. Furthermore, MOCVD is likely to maintain its dominance for 3-5 devices for the near future. For commercial production, there's no technological competitor under current development that can compete in uniformity, device performance, and cost today. So let me return to the alloy road, which allowed us to get this far, and MOCVD, I claim, is the ideal technology for traveling on the alloy road. Thanks for your attention.
We want to open the floor for questions. If you have a question, please feel free to ask it. I believe there's a microphone on both sides of the room if you'd like to use that. I'll get started. I have a question for you.
Sure.
Being a silicon man, I have a question about what technology, how would you best integrate MOCVD devices with silicon devices? What do you see as being the strength of silicon moving forward?
Well, as that cartoon showed, I think you're going to end up with this SOIC approach where you've got optimized 3-5 MOCVD components embedded on the chip, three-dimensional stacking. We've optimized silicon. We've got most of the technology for optimizing 3-5s. We can individually optimize those, and then it becomes a packaging problem, which is SOIC technology. So I think that's the way to go for now. Of course, there was an earlier concept. We were trying to grow 3-5s on silicon epitaxially, heteroepitaxially. That never became viable because of defects and dislocations. So today you can actually remove epi from substrates, 3-5 epi from substrates, reuse the substrate, implant your thin film 3-5 components onto your silicon CMOS and reuse the substrate. So bring the cost down even further. And that technology, substrate reuse, is already in production for thin film heterojunction solar cells. So those 3-5 multi-junction cells are actually removed substrate devices in some commercial applications where, mostly space, where weight is a big factor in launch capability. So the technology exists to remove fairly large areas. I think 6-inch now is demonstrated, 6-inch epi off of 6-inch substrates and reuse the substrate, maybe 5 times.
So it sounds like maybe silicon will be a base substrate for multi-chip modules.
Right, yeah. I mean, this is just saying, today I'm going to use this gallium arsenide chip instead of another silicon chip for my SOIC. It's the same questions that arise about alignment, interconnect contacts, thermal budget, all of those things that become practically difficult. But there's that whole technology is going to shift. SOIC will become the integration platform for 3.5s and silicon. Probably already has, quite frankly.
Other questions?
It was a great talk, by the way. Thank you. I was just wondering, kind of as 3.5 technologies, can be co-integrated with silicon, what your opinion is of, I guess, like silicon uranium HPPs and their place in the trade space. If you can just replace their traditional use case with 3.5 devices, do you think heterostructured SIGI HPPs are going to?
There'll be a lot of places for SIGI because it fits the CMOS technology ideally, or almost ideally, right? And it works. It's already been in the industry for 25 years or more, right? Since I don't know, maybe IBM was one of the first to commercialize it. So I don't see that's not going to go away. It's where you really need the highest possible performance at the lowest energy cost. So, for example, if you're doing quantum computing, how do you get information from your qubit out of this refrigerator into some other platform like a silicon IC? It costs energy to transfer electrons, so you got to use light. You got to use light. You got to use laser diodes at 4 Kelvin or sub 4 Kelvin, whatever, to bring light out and have a low energy picobit per joule kind of picojoule per bit kind of cost structure. So even if you transition all your computing to superconductors, to superconducting quantum computers, you've got to solve that energy problem. And the only way to do it is not with electrons, with photons. Zero mass bosons. So if anything, the next generation of computing, if it's quantum computing with cryogenic technology we know today, it's all going to be enabled by 3.5s. It doesn't do much good to do your computing at 4 Kelvin and never get the information out to humans. It's nice the circuit knows what the solution is, but you don't know what the solution is. So you got to get information out, and except near a black hole, where we still don't know if we lose information near a black hole. But anyhow, it's going to require MOCVD, low-cost VCSELs, cryogenic VCSELs, probably like these devices in your Apple iPhone, to do that.
Question up here at the front.
Thanks so much for your time and just giving this presentation. I have a question about kind of the skills you see as necessary to keep driving innovation forward in the optoelectronic and photonic space. And I guess, where people should be thinking of kind of, where to concentrate their focus on driving the technology.
Well, obviously, it depends on what your focus is. Are you looking about volume production or the next best innovation? So we've got lots of things being worked on. We can still learn a lot about the nitrides, for example. There's still, and Dr. Doolittle's group's working on that, is using wide bandgap materials like aluminum nitride for electronics. And that brings us another power advantage. But it's still an FET. It's still the same majority carriers, minority carriers, field effects. All of those things have to be understood in that material system, which is, the fundamentals will never go away. We're still using the same Shockley equations he rapidly wrote down in January 1948. And we're still using, if you will, a motor carrier injection for a lot of devices at least. So where's the next thing? Obviously, quantum computing is the world's next best thing. We'll see. The only question I have is if you're robot has a quantum computer in it at 4 Kelvin, does he have a little tank of liquid nitrogen he walks around with? I don't know, right? Maybe we'll have room temperature superconductors, and then life will be good. And we don't need no stinking semiconductor anymore. Everything's niobium or something. Graphene, maybe, I don't know. So yeah, there's still, the graphene is another area that 2D materials that are still on the cusp of becoming the next best thing. So I wouldn't throw them out as a non-starter, but if you look at what TSMC, Intel, others, Apple's design team, they're not designing with graphene, as far as I know. So that's another area to work in. I think 2D materials and wide bandgap semiconductors are the next things that probably will soon come into commercial use in a larger scale. Oh, energy is a big problem. As you know, we have a few tankers moving around in the Gulf and near the Strait of Hormuz, and energy is what drives our world today, and can't live without it. So we got to use it much better than we have. And I'm not saying MOCV is a solution for global warming, but it's certainly a possible contributor to improving our energy use and efficiency.
All right, it's time for one more question. If there's one more. Yes, sir.
Thanks for the great talk. So, kind of a question. I see that the gallium arsenide and gallium nitride has been studied pretty well over the past decades. But I also saw on the slides that silicon nitride has been sort of studied in recent years. I'm kind of curious, what's your opinion on the future of the silicon carbide?
Silicon carbide?
Yes, and especially its application in the photonic integrated circuits.
PICs in silicon carbide, is that what you're saying? Photonic integrated circuits?
Yeah.
Okay, well, silicon carbide is a real material. It actually can be dug out of the ground in some places, called carborundum. You can make moissanite. Those are crystals you can dig out of the ground. You make fake diamonds, moissanite. Silicon carbide has a very good future for diamonds replacement. Electronics, clearly a viable material. Wolf Speed, which originated at least in Raleigh-Durham, North Carolina, and NC State, is making 8-inch diameter silicon carbide wafers and epi, and making power devices for 1200 volt plus electronics. So it's a real technology. It's being developed in China and Japan as well as Europe. So I'm sure it's going to be useful for those kind of high voltage applications like vehicles and possibly the smart power grid. The nice thing about silicon carbide is it's got an oxide called silicon oxide. And so CMOS sort of moves, I'm not saying trivially, but moves in a logical way to silicon carbide from silicon. Especially in smart grid where cost matters and you've got big towers and they're not moving and they don't require the highest efficiency, it will become dominate. I'm not sure about iPhones and those kind of things that rely on weight and power consumption. You can still beat silicon carbide with gallium nitride. And when the cost comes down low enough, the equations are unavoidable. You're going to put GaN in some of those highest performance devices. Silicon carbide also has such good thermal properties that it might go into high temperature applications, engine monitoring for combustion engines or even nuclear power plants. We look like we're going to need more nuclear power plants So they should be smart nuclear power plants. So silicon carbide may be a good solution. It's probably pretty good in rad hard applications as well. So it'll have a role to play, but and critical probably in power grid, but not in. It'll eventually lose the vehicle market and the smartphone market and the computer power supply market because of efficiencies. Also, there's no light emitter, right? You can't make a laser out of it. It's indirect band gap, so you're stuck with, as far as light emitters, you're going to have to use GaN.
Thank you very much.
And thanks to our sponsors, Jim and Helen Carreker. Thanks for coming.